So I applied pressure to one side of the die. The difference in pressure caused uh, a certain amount of electricity to flow, or like purple electricity here. Um, but what I want you to pay attention to is the speed or the flow rate. Okay, I'm going to go ahead and load this the same amount of dough or electricity, we'll say. This would be a quantity of electrons. And this time, I'm going to push it through a die which is looks like it would provide a lot more resistance than the flow to this one compared to this one here. And so I'll go ahead and apply pressure, and I want you to keep 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 track of time. I'm pushing, so let's see, pressure. This would be voltage. I'm going to press and apply pressure, which is think of it as synonymous with voltage. 1, 2, 3. Okay, so we see that that did definitely take more time than the die with the less lower resistance. What was different? I pushed the same amount of dough through the die. So here's where a lot of people get kind of confused when we talk about current, electric current. It's not just an amount of electrons. A lot of people say current's the amount of flow. Well, no, I'd like you to be more specific and think of it as a flow rate. And if you were to compare that with water flow, think of it as the rate of flow, the speed that the water is flowing through your garden hose, compared with, for example, a fire hose. Certainly that water is much faster. It shoots out in a much longer stream. Obviously, it's under greater pressure too. I have another comparison here, basically a way to show the same concept using these little tubes. I have a tube with a lot of resistance here. I have a tube with, as you can see, virtually no resistance. Usually I like to embarrass students and have them come up to the front of the class and do this. I'll put two students side by side and challenge them to push this electricity out. We'll call it electricity at the same rate. And of course, it can't really be done if they push as hard as they can. The purple one is going to certainly take a lot more time because it has more resistance. So if I apply my pressure, we'll call it voltage. I apply pressure now. 1, 2, 3. Okay, and I come over and do this one, applying pressure or voltage. 1, 2, 3. Okay, certainly I push the same amount out, which again, I don't like to think of current as amount, but think of it as flow rate. So the rate of flow is current, the pressure is voltage, and what changes the rate of flow? Resistance, or if you want to think of it as friction. So remember, whatever happens in Crop's class stays in Crop's class. You know, I don't mean to embarrass you by talking about dough and kids' toys, but I want you to remember this throughout the semester. Voltage is pressure, and it's more specifically the voltage which moved our dough or our electrons was the difference in pressure. The higher pressure on this side, lower pressure on that side. Those electrons or that dough moved, and then how fast it moved is, in addition to being a function of pressure, is also a function of resistance. And this relation is referred to as Ohm's law. And the formula for Ohm's law is E equals IR. Unfortunately, multimeters don't show those specific letters necessarily. You're not going to see an E on a meter, you'll see V for volts. And so I teach Ohm's law simply by saying volts over ohms equals amps. And ohms, in this case, think of it as the Greek letter omega, which is in the literature in your class.